Hello everyone, we're going to be starting lesson 6. By the time you're watching this video, in support materials, you'll be seeing these two tables, the SI base and derived unit table, the metric conversion table, and then you'll also be seeing the PowerPoint for measuring. So I'm going to open this first. So a measurement is a comparison of a dimension of an object with an appropriate standard. Meaning you take whatever you're measuring and you compare it to a standard. I want you to imagine if we're trying to describe how tall somebody is, and you describe how tall they are based on the height of your dog, and I describe how tall they are based on the height of my desk. If we're both using random standards, you go, oh, that guy is, 7 dogs tall. Meaning if you stack your dog on top of himself 7 times, you talk about the guy's height. I don't know how tall your dog is, and if I go, oh, he's 3 desks tall, you have no clue how tall my desk is. So if we measure stuff and we don't have an agreed standard, it just won't work. And then anything that you can measure, so any property of matter that can be measured, is called a dimension. And then a unit is the most technical definition is one of something of a given dimension, right? So a foot is an example of a unit. It's one of a certain length. All right. So in the questions here, which definition is this speaking of? Go back and look at that slide. You'll see it's talking about comparing an object with a standard is a measurement. Which of these is not a dimension? Which of these is not something, look at the definition, which of these is not something that can be described as a measurable property of matter? So you can measure the volume, you can measure length, you can measure height. You cannot measure how annoying your brother is, even though maybe you think there is a measurement for that. What would be the consequence if nobody agreed on a scale for measurement? It's kind of what I just described, where if you're measuring based on the height of your dog, I'm measuring stuff on the height of my desk. Do either of us know what the other is saying? Imagine trying to build buildings, if each person has their own way of describing how long something or tall something needs to be. It would just be ridiculous. All right, so back to the slides. To make a measurement, we use instruments, which are anything that help us measure. This could be marking on a wall. This could be a ruler. In order for an instrument to be worth something, it has to be calibrated. With this, I think of a scale. You need to calibrate a scale regularly in order for it to be worth anything. And then you have to have a scale on your instrument to match what your units are to the thing that you're measuring. All right, so there's a system of measurement called the metric system, which started off with just a meter and a kilogram. But what we did is we measured everything by multiples of 10. I do not like the system that the United States uses, because for us, it's just completely random. There are 3 feet in a yard and 12 inches in a foot. And most people, if I ask them to compare cups and quarts and pints and gallons, most people don't even know what those dimensions have to do with each other. Our system is just all over the place. I much prefer the metric system, and I wish we would transfer the metric system, because everything is based on a multiple of 10. That's what's so nice about it. But with the metric system, we wanted to use that 10-base system to other dimensions. So there's the SI scale, which has 7 base units, which describe 7 dimensions. But because those 7, so actually let's go ahead and look at them. So in order to see these scales I'm talking about, if you go right here, SI based and derived unit table, here's your base units right here. You can measure length with a meter, time with a second, mass with a kilogram, temperature with Kelvin, electric current with an amp, luminous intensity with a candela, that's light, and the amount of a substance with a mole. Can you guys think of anything you'd want to measure that you can't measure using these? Hopefully you can, because there's quite a few. Do you see how you'd measure speed on here? No. Speed, you'd have to do some type of distance per time. Think about how we here use miles per hour, but you could do meters per second. Okay, so speed requires a combo of these, but not one of these. So that's just one example. Density, there's all sorts. So that's why we do have our base units, 7 base units, but that's not enough, so they had to up it to the derived units. So look at some of these derived units. Let's go to something like force. If you want to measure force, how hard something is pushed, we describe force as a Newton, and what a Newton is it's a combination of base units. It's a meter per kilogram divided by second squared. So this is the combination of base units that get us to a Newton. Okay, so here's an example of, these are a bunch of different examples of derived units. All right, so look at the table to compare base and derived units. So an example, we can measure some of the stuff with base units, but thermal energy, for example, to measure that, we have to do kilogram, meters, and seconds in this combination. So kilogram per meter squared divided by second squared, that gets us to a joule, which is how we measure thermal energy. So you need to be able to recognize these derived and base units. The main thing I want you to be able to do is just tell when something's derived and something's base. And here's what it will look like. So let's go to this. So notice this, just a meter is a base unit. A kilogram is a base unit, and a second is a base unit. But when you combine them, you get a derived unit. And what derived unit does that make? Well, in order to figure that out, let's look right here. What derived unit is a kilogram or a meter times a kilogram times a second to the -2? That would mean divided by a second squared. What does that look like? Well, we're looking for meter, kilogram, second to the -2. Here we go. Meter times kilogram to second to the -2. So this is describing a Newton. Okay, so see this? Which one of these is this? This is a Newton. What about right here? Second to the -1. If we do the math on that, that's 1 divided by a second. So where do we see S -1? Down here. Oh, right here. Let's go with this. Right here. S to the -1, that is a hertz. So it's a hertz. What is this right here? Meter squared, kilogram, second to the -3rd, amp to the -1. Let's find that on here. That is the electrical potential difference, or electromotive force, also known as a volt. Meter squared, kilogram, second to the -3, 8 to the -1. So see, it looks complex, but just use this table and you can recognize those things. So that is a volt. Okay, now the last table I need to show you. So that's what we have here. And the last thing we get to is the prefixes you can put in the front of any of these base or derived units. So you could have like a gram, and to describe an amount of grams, you could call it a milligram, centigram, kilogram, hectogram, decagram. There's all sorts of types of grams. I don't expect you to memorize the whole scale, but you definitely need to have milli, centi, and kilo memorized, because those are the ones that are going to come up a whole lot. Those are the most common, so make sure you have those memorized. But with most of these, the more you use it, the more you'll memorize them. So let's go ahead and look at that table. This now is the table right here for metric conversions. I've given you this table where, look, it says 1 tera of a liter, meter, gram, whatever your unit is 1 followed by 12 zeros of whatever that unit is. Let's go down small. 1 decaliter or 1 decameter, 1 decagram is equivalent of 10 liters, meters, or grams. Down here, this is where it gets small. So a liter is the same as this many nanoliters, or a gram is the same as this many milligrams. Okay, so that's how we do that. So let's go ahead and look at these questions. A decagram is how many grams? Look right here. 1 decagram is what? 10 grams. 1 megameter is how many meters? So 1 megameter is, look right here, 1 million meters. You guys see how you do that? There are how many centijoules in a joule? So there are 100 centijoules in a joule. And then there are how many milligrams in a gram? Look right here, milligrams. There's 1,000 milligrams in 1 gram. All right, so today I just wanted you to get used to using those tables. And then tomorrow we're going to do some math that at some points will require us to look at this last metric conversion table. All right, so as always, email me if you have any questions, and I hope you guys have a great day.